All right. So yeah, thanks, Annegret. Let's do the second part.
Okay, I was just going to say a little bit more about these 2 points, and then I'm going to give my presentation about what I have planned should be the second part. Okay, so I'm just going to give some examples so that you have seen them. Important solutions to the Einstein equations. This is of course what physicists have done first, derive explicit solutions, and we are mostly going to sequence the vacuum case. Also, I'm going to say a little about some other solutions as well. So the first one is of course the Minkowski spacetime, just a flat one. So in particular, it's Ricci flat. And the second one is the second most important one, or the most important even for mathematical relativists, the Schwarzschild solution, which was also independently found actually by Burtscher, a student of Lorentz, in 1916 already. This is a solution of a static black hole, and looks like that. Of course, in some coordinates. Symmetry. Metric. And this is m is a parameter, so this is called the mass, positive. And this describes so this is spherically symmetric, static, asymptotically flat, and I'm not going to define that now. But it describes the gravitational field outside a spherical body or a black hole. So it's mostly used to model black holes, but you can also use it outside of a star. Star. And maybe just to say a little bit about there's an important result actually that is true in the Ricci flat case. And I had a bachelor student who once wrote a bachelor thesis about this, is that as soon as you have a spherically symmetric solution to the vacuum Einstein equations, you automatically know it is this form. It's automatically static and asymptotically flat, and exactly of that form is a one parameter family. So this is a very rigid, the spherical symmetry in the vacuum case is very rigid. The only solution you get is essentially that one. And M equals series, of course, is Minkowski spacetime. Well, yeah, it's well PDE, but yeah, you have a spherical symmetry, gives you a special foliation, and then you just plug it in the equations, and then you see that that's what comes out of it. Yeah.
And when people talk about spinning black holes being a problem because then they're not going to be symmetric.
Well, this
anymore,
is,
they're going to.
Yeah, they have to be. Yeah, they're actually symmetric. Yeah. So this is the core, but this is the theorem that states that's called Birkhoff theorem. And actually, there are several other people before Birkhoff who proved it, but Birkhoff was the most important guy, so it's named after him. But so it's a very old result. And Birkhoff theorem says that you have a spherically symmetric solution to the vacuum Einstein equations. It's automatically of this form, and in particular static and asymptotically flat. Yeah, I mean, basically that Schwarzschild solution. So in a sense, it's very difficult to study solutions to the vacuum case, because you have to study solutions that are not in any ways have any nice symmetries. You have to be very general. And Schwarzschild solution models a black hole. And you can already see that apparently in these coordinates, it looks like you have two singularities, one at r equals 0 and one at r equals 2m. But the 2m is just a coordinate singularity. But it is the event horizon. So for a very long time, people didn't realize that r equals 2m isn't actually a singularity. It's just a bad choice of coordinates, and you can change a coordinate system and you will see nothing happens there. But of course, it still has a physical meaning because the directions of the light cones change, and then you have a black hole. And but there are other black holes, rotating ones, which are called the Kerr solution. So this is a rotating black hole, and this is what we expect to see in the universe. And then you can also have what's called the Reisner-Nordström solution, which I will also mention later. This is a charged black hole or a charged solution with so essentially the same form plus a charge. And the Kerr-Newman, which is also rotating and charged. So they have all explicit solutions. And another important class of solutions is the FLRW solution.
And
Yeah.
these are all globally hyperbolic?
Well, yeah, and the exterior, yeah. Yeah, if the mass is positive or greater equal to 0. I will later say something about when they are not, then you have a naked singularity, and then it's not.
But this makes no distinction for bigger plus smaller masses, right?
Yeah, it works for any mass. Yeah.
So it's not really a black hole problem.
Exactly. It could also be the exterior of a star. Then if the density goes to 0 at some boundary, but these are generally very difficult problems because you kind of have to assume a free boundary problem. So the boundary is not fixed in a sense. You have to allow it for it to be flexible, and that makes it very complicated if you want to really study stars. So FLRW, these are called Freeman, Lemaitre, Watson, Walker spacetimes. And these are particular kinds of warp products. So matrices are this simple form. And then you have here a Riemannian metric of constant curvature. So elliptic, hyperbolic, or flat Euclidean space. And then, of course, the Einstein equations reduced to ODE for A. Okay. But these are very important in cosmology solutions. So this is just I wanted to write down some very basic solutions. And these are actually a very big class of. And I mean, if you want to study anything more complicated than Minkowski space, this is the next thing you're going to do. So these FLRW solutions. And I wanted to say a little bit about the initial value formulation because it's also related to this concept of globally hyperbolic and this Cauchy surface that I have said before. Okay, so and let's just stick with the Ricci equals 0 case because that's already complicated enough. If you want to, so okay, I said it's a second order differential equation for G. And you can see it's a differential equation, but how do you solve it is the problem. And how do we even pose an initial value formulation? And for that, you need to pick suitable initial data. But essentially, there's nothing that you should start with generically. And so you assume that you have a globally hyperbolic spacetime in which you can pick a Cauchy hypersurface. And then you restrict your Lorentzian manifold to this hypersurface, your Lorentzian metric to this hypersurface. You'll get a Riemannian metric there, and but not just any. You cannot just pick anything because it comes from a space-time, from a four-dimensional object, and it has to satisfy certain embeddings. And these are the Gaussian-Godazzi equations that you have maybe seen already in Riemannian geometry. So if you pick, so usually the constructions is the following: you assume you have a space-time solution that satisfies the Einstein equations, and then you pick a Cauchy hypersurface. And on this, you have induced a Riemannian metric and a second fundamental form. And those objects have to satisfy the Gaussian-Godazzi equations together with, that gives the Ricci equals 0 gives you additional constraints. And so if you want to pose an initial value formulation, what you ask for is you start with a Riemannian 3 manifold, or I mean, it could be n-dimensional, but plus, Riemannian makes it the metric and second fundamental form. But as of now, we don't know because second fundamental form only makes sense if you have a bigger space. So we assume this is metric 0, 2 tensor. And then Yeah. So they are admissible if they satisfy the what's called the constrained equations. These are 4 equations from the Gauss-Bonazzi equations, and I'm just going to write it down so that you see how they look like. Okay. Now everything is with respect to sigma, of course, because we don't have the G. This is called this is a scalar equation. This is called the Hamiltonian constraint. And we also have a momentum constraint, which is a vector equation. These are 4 equations that such an initial data set have to satisfy in order to be even admissible to leading to a solution to the vacuum Einstein equations. And if it's not vacuum, then of course you have here non-zero in. And these are called the constraint equations, and you can, it's not obvious what they are, but one can show it. So they're underdetermined, and you can rewrite them as a system of nonlinear elliptic PDEs. There are different ways or methods of getting solutions. So there's called, for example, what's called the conformal method or the sim sandwich method. And nowadays what people are also do, so this is a result by Carlotto and Schön, that they patch together solutions. But this is not, I have never really studied this, but this is what you have to assume from your initial data, that they satisfy the constraints. Otherwise, you have no hope of deriving a solution.
We working here analytically or
Yeah, mostly smooth now. Yeah.
smooth, not necessarily analytic?
No, not necessarily. Okay, so people like Schön and all of his PhD students basically studied this very extensively. And there's actually a recent, so if this is something that interests you, there's a review article in what's called the Living Reviews in Relativity, written by Carlotto Schön from this year. So this is about 200 pages. So he's a professor at ETH Zurich. Okay, so once you have kind of a suitable candidate for your initial data, you have to then, of course, still show that you have solutions. And this is a famous result from 1952 of Bianchi, which, by the way, is still alive. I think she's 98 now. But this then basically uses more or less, so that the real difficulty is this reformulation that took a while for people to come up with, and then you usually use a standard hyperbolic PD theory, at least for the vacuum case, to show that for such admissible initial data, exists unique up to diffeomorphism, maximal. This is actually, that it's maximal has been derived later, but I'm gonna state it here now. Unique maximal hyperbolic development. So that MG So that is multi-diffeomorphic to a Cauchy surface, or is it essentially a Cauchy surface? And of course, the Riemannian metric is just a restriction of G to the surface, and K is the second fundamental form. So they are really what they should be, basically. And the way this is derived is based by rewriting the vacuum Einstein equations to a system of quasi-linear hyperbolic PDEs. The basic idea is the Ricci curvature is second order, but it's not necessarily a wave operator. So one has to make a particular choice of coordinates, and these are called the harmonic, well, one chooses harmonic coordinates. And then one can essentially show that one gets something like that. Quasi-linear system of hyperbolic PDEs. And then one can apply the standard hyperbolic PDE theory and get a local solution and extend it. So it's not really a proof, but just that you get an idea that in solving the Einstein equations, there is an elliptic theory involved and there is a hyperbolic theory involved for the evolution. Are there any questions about that? And of course, if there's matter, it's you have to reprove all these results in a more complicated way.
So, which are the tools used here for the proof?
Sorry, the tool.
It's in one of the
This is
proof.
basically quasi-linear hyperbolic PDEs. This already existed at that time. I mean, you can then show that you have smooth initial data, you get smooth solutions. And actually there is a recent conjecture. Well, it was already resolved in 2012, but then it was published in Invenciones in 2015 that was called the L2 bounded curvature conjecture. That actually the only information that you need for your time of existence is some L2 bounds in the curvature of your initial data. And then of course these results are much more complicated. So if you kind of it depends a little bit on your class of regularity of your initial data, how complicated the results are. But there's the latest and the last result in this is the L2 bounded curvature, now I should call it theorem. By I'm trying to remember what Yansky and Seftel. And this is essentially their result tells you that this theory that you apply here was linear hyperbolic PDEs. It's very general, but the Einstein equations are more special. And their result kind of tells you are a little bit more special because you have this particular null structure of the PDEs that you can also use. I have actually, when I was a postdoc in Bonn, I have taught a master course on this result without the maximum. But it was a whole course to to establish all the theory for that. It's not, yeah, it's not anything trivial. That, yeah, it requires a little bit of background. So you need to know about symmetric hyperbolic systems, and then you just need to rewrite it. So you need to know a little bit about that, and then you can use that theory.
Yeah. But in this case, you said so the resulting space has Ricci zero? No.
Yeah.
Ricci space.
Yeah. Sorry, I didn't even write down. So that yeah.
And is there like an analogous result if you say something about T or?
Yes, there are not, but you have to derive these results separately because then also the matter has the energy momentum tensor T also has to satisfy additional equations. So it's more complicated, but they're analogous results, yeah.
And the techniques are maybe similar?
No, they are usually quite different. No, they're more involved. So as I said, for example, for fluids, it was a completely different theory. So I use a series of continuum mechanical hyperbolic conservation laws to solve it if you are in the case of fluid. And then the regularity of the solution is also lower. So the result is not quite the same. But they're of similar flavor in a sense.
So if I understand correctly, so to solve these equations,
Yeah.
you already need initial conditions that sort
Yeah,
of-
they are good. Yeah.
that are good.
Yeah.
And that's very different than, for example, the wave equation, something like this.
Yeah, because
you
for
can
the
do
wave
anything.
equation, you could use anything. Yeah.
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 Okay.
But in a sense, I mean, this is the whole problem with the Einstein equations that, you kind of determine the space as you go along.
Correct.
Like for every other partial differential equation, you start on Rn and you remain in Rn and nothing changes there. But here, like it's like all coupled, the space isn't there. You're kind of producing it as you go along. And that makes it very complicated.
But that's not really the case in the globally hyperbolic case, is it?
Well, you assume that it's there, but you still, I mean, you don't know how it looks. So,
Okay.
I mean, you kind of assume that it's there, that it makes sense, but
It's kind of understand the point because of course you can get a solution and
Yeah.
then you see how it evolves and if I develop some similarities.
well, this is
Yeah,
without
so-
singularities now. This is not talking about singularities
It's
at all.
not about
But I
similarities.
have in my PhD derived the result about the singularity formation.
Mhm.
And for that, you need to be a little bit careful about what kind of initial data you use. I mean, you cannot just say, I mean, for example, if I use just flat data, R3, then I will just get Minkowski space. No, there will be no singularity at all. And people have also shown that Minkowski space is nonlinear stable. This is a result from 1990. Christodoulo Kleinerman, which was a whole book of more than 500 pages, show that Minkowski space is nonlinear stable. So if you choose initial data close to the initial data of Minkowski space, you get something that's also free of singularities and close to Minkowski space. But actually what this year happened, and I don't know if you've seen it on arXiv, people have proved finally after 30 years that the Schwarzschild solution is nonlinearly stable on about 600 pages. Yeah. And they're also, I mean, not complete, but almost complete results for nonlinear stability of the Kerr metric, which are more than 800 pages. I haven't read it yet, but
then there's something else like the equation determines this like there was a lot about derived information, but like you start
now you
data-
perturb a known solution. These results are about stability of known solutions. And the result that I have derived, and this is also, I mean, I'm not the first to derive this, but the first person to derive formation of black holes was Christodoulo. And he had a series of papers which were published in the annals in the 90s. He had results on the scalar field model, so where the energy momentum tensor, the T is kind of a scalar field, which additionally satisfies the wave equation. And he showed that he can prove the formation of trapped surfaces, which are part of the singularity theorems that kind of determine that, yeah, it's complicated, but it's something that kind of signals that you have a black hole.
Nothing comes out of it, right?
Yeah, but yeah, well, it's complicated because the singularity is very complicated. The singularity theorems, there's three conditions. Yeah, one is a trapped surface, then you have a non-compact Cauchy surface, and you have a converging condition that is usually described by non-negative rigid curvature in different directions. And these analytic PD results, they kind of show that you can form a trapped surface. So you will start with initial data, and then at some point in the future, you develop a trapped surface. This is a two-dimensional space-like surface. And but you have to kind of use very specific initial data to be able to produce such a result. And so there are several other papers in matter. So he has also derived a result in vacuum using gravitational waves. And this is my PhD advisor result for fluids, but in this case, it's spherical symmetry, because if you have a matter model, you can use symmetries, and that makes it easier. And you can show that you can kind of pick initial data that are almost static, but in some region there, you have a lot of data. And then, so it's kind of like having a kind of a shell of matter, if you want. And then you can show that you have, yeah, this kind of bulk of matter produces a trapped surface. And yeah, well, mathematically, you do that by picking a coordinate system that kind of models whether you have a trapped surface or not. So in the, yeah.
But for this thing that you have there,
Yeah, this doesn't say anything about that. No.
nothing about that, right? So,
No.
so it's about like what you're saying, maybe a metric,
Yeah.
first second
Yeah.
formulated form.
Yeah, it doesn't tell you.
Possibility.
Yeah.
Then there exists globally hyperbolic development.
Yeah.
And is that in n times r? Like you just like is it a sugar enablement type of thing? Like or in this process you actually have to complete some topology.
Well, okay, the topology, yeah, the topology is usually very trivial. So we just use like R4 or something like that.
Okay.
I mean, there are people who sometimes, especially in cosmology, they study things on the torus and something compact, spatially compact. But most of these results completely ignore the topology, I would say.
But this is more like because you have the Cauchy surface already, so in a way the direction is missing time. Right? So you can
Yeah,
also
exactly, yeah.
extend it on time, and then but
Yeah.
so it never kind of branches out or anything.
No.
It remains a bit like a product or a vibration.
Yeah. Yeah, it's a bit, yeah, and this also, I mean, essentially by this globally hyperbolicity that kind of imposes that already, that you have a product, yeah. But of course, a product in a manifold sense, right?
Right.
How the metric looks like is still more complicated. But they're also in the splitting result, actually, they also have a very particular, I mean, how these metrics then look like. So you can see a little bit more.
But and what this word maximal, I mean, because
Yeah,
Gil was
maximal.
saying that it was a tubular neighborhood, but if you say maximal, it cannot
Well,
be
maximal
considered
means
stuff.
that it cannot be extended as a globally hyperbolic
Okay.
manifold.
Okay.
So if you would extend it, then it would no longer be globally hyperbolic or something else would go wrong.
But is there like what you mentioned that before? Once you have globally hyperbolic, there's some completeness associated to it as well, right? So
Yeah. So essentially, it would say that you stay outside of troublesome regions. You don't look at those. So from a geometric perspective, you can look at those problematic regions more easily because you don't need to make these strong assumptions. But for the PD theory, you need this globally hyperbolic, otherwise the initial data doesn't make sense.
So if I was to pick in constant space and just restrict myself to time between -1 and 1,
Yeah.
is that globally hyperbolic?
Yeah, I think it should be if you include the boundaries. Yeah.
Oh, to include the boundaries.
Yeah, because otherwise you will not have the closed the causal diamonds will not be.
Diamond always has to start like it doesn't reach one.
Yeah, but yeah, it has to be compact. Yeah.
But then I don't understand this maximality because it doesn't look very maximal. If I
Well,
can add a bigger
but you only asked about globally hyperbolic. I mean, anyhow, this is actually a result. Yeah, this is actually a different result. This is a result from 1969 with a different. So this is a zero. This is not. It's not quite the same. It's not quite the same proof and idea. Okay. This I just wrote there because yeah. You can also get it, but it's not really included in this procedure. Okay. Should I say a little bit more about the presentation that I had also prepared? Look, I mean, this is just to show that because this is like nothing, it's about my stuff.
Yeah.
Yeah, please.
You can also put off the lights.
Yeah. Let's see. So this should be project.
So I mean, generally, I do like black holes and so on, but I think there's a lot more that one can study and understand, and this is a little bit related to that idea.
How do we make full screen here?
But there, maybe there's.
Or maybe we can just open in Acrobat, right?
So, I mean, most of the universe doesn't consist of black holes, and we don't see black holes on a daily basis. So and the only nice thing is that, you know, mathematically it could be proved that they exist long before people believed that they exist and actually saw them to exist. And I think that's one thing where mathematics has really, you know, advanced this theory.
Control L.
Let's see. I'm also not wearing glasses, so yeah, okay, Control L, that feels more safe. Very good.
Okay.
And the
Yeah.
light. Oh, yeah.
Yeah, so now I'm going to talk about something that are also singularities or modeled as singularities, but not as singularities that are hidden behind some event horizon, but naked singularities. And of course, this is just a model, so this is not. No, nobody says that you know, particles are naked singularities, but it's kind of a way to describe particles. Because in relativity, what is difficult is, of course, you have isolated systems and you have mass for that, but you don't have like, you cannot assign mass very easily to different objects in one space because you only have a notion at infinity for that. And there's similar problem with describing things like center of mass, which are all very easy in Newtonian theory, but are very, very difficult in general relativity. And so a way to model the particles and several particles at once is one that I'm going to describe now, and it's not my own. In fact, it actually goes back to much before. So the basic idea is to try to understand, well, how do particles move in general relativity? And the textbook approach is to say that they are actually test particles. So basically, they don't really exist, and they just move along geodesics when they are uncharged. And whether they exist or not, it doesn't have any effect on the geometry. Okay, they're like freely falling particles moving along geodesics. They don't have a weight, and well, you also cannot assume a charge. Otherwise, it's different. And one such example is what's known as the photon sphere around the Schwarzschild black hole at the radius 3m, where photons are kind of accumulate and move. But if you want to take real particles, or especially if you want to take particles of similar mass, of course, if you have one very heavy object and one very light one, then you can say, well, I just have the gravitation of the Earth, and you know, I have stuff moving around it. Then it almost moves on geodesics, and I don't have to worry about it. But if you have two objects that are almost the same, then it becomes complicated. And the only thing that's really known is numerics. But there's also another approach, and that also goes back to Albert Einstein, who said that in 1926, already tried to think about ways of deriving equations of motions for material points by describing them as certain kind of singularities. And there's a long history and a lot of literature about it. So the first paper is from Einstein, Infeld, and Hoffman in 1938, and then there's a second version of it, a more refined paper, and Infeld's student Wallace also wrote a version of it with charge. And there are several mathematical problems, because what they basically do is they use linear approximations, and they're not completely mathematically precise. And there are a lot of problems with their derivations, and there are many mathematical papers or mathematical physics papers trying to fix that or trying to come up with alternative theories. And well, I would say that yeah, our approach is kind of tries to go back to the original one, but try to make it more rigorous. And so what is the original idea is that when most models the kind of motion of these particles as one-dimensional time-like singularities. And that is should happen in a general electromagnetic theory. So we wanna include charge as well. So we take the Einstein-Maxwell equations, where you now see that the right-hand side is an energy momentum tensor for that satisfies additional equations. Here the Faraday tensor and the Maxwell tensor. Away from these singularities, and the second Bianchi identity, which is what I said, actually comes from this variational approach as the conservation law, should then somehow describe the equation of these equation of motion for these particles. And the singularities themselves are the sources and the sinks of this electromagnetic field. And as I already said, this initial papers were a little bit not so rigorous, and there are certain problems with that. And another problem is actually that they also made, although they have themselves worked on alternative theories, is that one cannot actually use the linear Maxwell equations, because those are ones for which the self-energy is infinite, and this would lead to non-integrable curvature singularities. So we have of course curvature singularities because we have singularities, but they shouldn't be too bad. I mean, there should be, yeah, they should be sufficiently good so that we can kind of go through these ideas. And so the basic idea is that we kind of redo parts of these ideas and formulate a well-posed joint initial value problem for the motion of these particles, and at the same time also for these fields that they generate. So I mean, they contribute to the whole space-time. And the mathematical problems that are related to that is, well, the first one is more of a geometric idea problem, is that one has to choose the right kinds of singularities. There are time-like singularities with a certain model as an interior boundary. And the boundary data has to be sufficiently nice in order to be able to do that. And there's already previous work on that, and I will say more about that later. And yeah.
Can you say a bit more about what you mean by time-like singularity, or a picture of what I should?
Yeah, well, yeah, okay. So if you, for example, if you think of Minkowski space and you remove r equals 0,
okay.
In r equals 0 cross r, capital R,
So
then this will be, yeah, this will be like time-like. So it means time-like singularity means that, yeah, the space like geodesics and there, that kind of the orientation is time-like.
but can I think like it's maybe like kind of like a delta along the trajectory of a particle?
Yeah, that's the
That's
analogous idea, basically. Yeah, yeah.
Okay, thanks.
Yeah. But of course, we want to do it gravitationally, so it's yeah. But that's the idea, that you kind of, if I draw again this picture of, you know, I kind of think I have this singularity here, or here, and this kind of models the motion of these particles, but not as geodesics, but as singularities. And this is, of course, time-like because they're. But of course, you cannot really say that because the singularity is not part of the space, so it's a little bit difficult to use that correlation. Yeah, and then the idea is that so we kind of try to interpret it as a time-like boundary and not talk too much about singularity with certain regular boundary data. And that is exactly the problem of the original idea, that the boundary data was infinite. But we want to have it in regular data, and then we derive a second Bianchi identity with a differential curvature identity. I will write it down later. So that this, so that it holds. Yeah. So the question is, what kind of geometry gives you a good second Bianchi identity? A little bit related, and then that's the last question. Maybe I'm not going to go too much into that. But the last question is then find metro models that that allow for this, because as I already said, that the standard Maxwell theory gives the infinite self-energy, and that's not good enough for this approach. And so the key question is basically to understand for what conditions on the metric can I satisfy a weak second Bianchi identity, and how should such a weak second Bianchi identity even look like? And well, maybe I should break it. So, okay, second Bianchi identity is a differential identity for the Riemann curvature tensor, but I think of it in terms of the Einstein tensor, of course, in a contracted form. So you can think of it more of an implication of the Bianchi identity. Implies that the divergence of G is 0. And we want to incorporate the singularities themselves or solve it up to this boundary, up to and including this boundary. Yeah. And so we have like a preprint on the very basic version of that, of when it could hold in a spherically symmetric static case. So it's super, super simple. But it's kind of trying to make sense for what could one use in a theory that's dynamical. And so I'm going to say a little bit about how one can model these singularities, but this also goes a little bit back to other geometries that are present in general relativity, and then kind of show you how such a version can look like and when it works. Maybe the first part is most interesting for this talk because it also relates to other geometrical results in relativity. Okay, so here I wrote down again the Schwarzschild solution, but now you have to think of it with a negative mass. Okay, so it's still a solution to the Einstein equations, which equals 0, but it's different. No? One thing in particular is that I no longer have a coordinate singularity at 2m equals r because it's negative, so this doesn't occur. Radius is always positive. And so I have a global, so this is globally given in these coordinates, which makes it very nice. I still have a curvature blow up at r equals 0. So this is a blow up with r to the -6 here. And well, I have this time like singularity at r equals 0. And the total mass is negative, but yeah, this doesn't tell you very much if you don't know what the total mass is. This is what we mean here, the ADM mass. This is a geometric invariant for asymptotically flat spacetimes. And the question is first to understand, well, what does it mean that usually we always want to consider spacetimes that have positive mass or 0 mass, like Minkowski. So what should this even be geometrically if you all of a sudden pick a negative mass? And here I just want to give you some, yeah, this is related to some other results in relativity, some very important geometric results. And most of some of these results are only known for 3 manifolds, and they're only known in the Riemannian setting. So that's why I wrote here, we just pick a Riemannian manifold, 3 dimensions with non-negative scalar curvature, ADM mass m. So you can think of this as a conserved quantity at the spatial infinity. And you can have asymptotically flat is just basically so that this mass is finite. Otherwise, it would be infinite, yeah. And you can have 3 different scenarios. The first one, well, no boundary, a minimal boundary. So that means area minimizing. Or what the last one, which I call a ZAS boundary, which I will describe in more detail. So the first one, the no boundary case, is the case of the positive mass theorem. Because if you have these assumptions and you have no boundary, then the positive mass theorem of Schön and Yau and tells you that the mass is always greater or equal to 0, and it's 0 if and only if the manifold is isometrically Euclidean space. So this is an important result from 1980. It was shown for dimensions less than 8. So 3 to 7. It was shown by Witten in all dimensions in the spinor case. And the higher dimensions are still somewhat open. So there are preprints available since a few years, also by Joachim Lokap in Münster, who was the first one. And then Schön and Yau have also written a version for higher dimensions. But these results so far only exist in preprint form. So I don't know anybody who has read and checked them. But it's yeah, it's interesting development. The problem with higher dimensions is that there are singular sets and they become more and more complicated. So this is a lot about variational calculus and elliptic theory. And yeah, that's the problem with the higher dimensions are treating these singular sets. But this is a very important result. And if you stick to 3 dimensions, everything is known. And now the question is, if you have a minimal boundary, what do I mean by that? Is that, well, you assume that in addition to your assumptions, you actually have a boundary that is the outermost minimal boundary, so area minimizing, a compact boundary, which is total area A. Then there's a conjecture of Penrose that says that, well, it's a conjecture, but it's known in 3 dimensions in the Riemannian case. It's unknown in higher dimensions, and it's unknown in a Lorentzian setting. And it says that the mass is always greater or equal than the square root of A divided by 16 pi. And it's equal if and only if the manifold is isometric to an exterior of a positive mass Schwarzschild solution. And this was proved by Husken and Illman and Bray around 2000. Husken and Illman, they used the inverse mean curvature flow. And Bray used also the positive mass theorem to prove that. And finally, the last one, this is actually something that even many people in relativity don't know. This is a result of Bray and his student Jarigi. They show that, so now we also assume a boundary, but we assume a very different kind of a boundary. So we assume a compact boundary again. And this boundary should be what's called a 0 area singularity. So you can think of that if you remove r equals 0, then this is a sphere of 0 area as an analog. And the result shows that if you have such a singularity, which I will describe a little bit more later, then the ADM mass is always greater or equal than this SAS mass, which is also something I'm going to describe, and is equal if and only if it's isometric to the negative mass Schwarzschild solution. So these are some, I would say, these 3 are some very important geometric inequalities in relativity. But also more generally, you can think of it in Riemannian geometry. And as I said, like the Penrose inequalities is largely still open. And also this last one is also just hasn't also been investigated in much detail. So maybe ours is one of the first works that uses this. And so the question is, well, what is this kind of a 0 area singularity? How to describe it? And here's just the assumptions again. So assume I have a Riemannian metric and I remove this kind of boundary and I'm smooth outside. And then a 0 area singularity is exactly one of those where this boundary, if you approach it with some surfaces in a C1 fashion, the area of these surfaces goes to 0. Hence the name. And you can even describe it a little bit more, so make it more special. You can call them regular 0 area singularities if there exists what they call a local resolution. And a local resolution is something that's a little bit as a conformal compactification that one usually has at null infinity. So it kind of assumes that you have an extension and it's conformal to your original metric away from the singularity. And yeah, so think of it like a sufficiently nice singularity where you can sufficiently, in some sense, extend it so that you can assign data to it. And this is exactly also what they showed, that for such regular 0 area singularities, one can assign an invariant, which is called that SAS mass. And it's defined like that with the normal vector of this local resolution, and yeah, this extension of this metric. And of course, they showed that it's independent of the local resolution that one chooses. And so the point is that we kind of try to use these singularities because they have a very well-defined data assigned to them. But they are more special than just picking any naked singularities. They have to be of this regular kind. And then essentially what we try to do, because we're only in the static setting, so it's a little bit simpler, is to say that we have an admissible time-like singularity if on these slices it's exactly such a regular series area singularity and the boundary data is negative. This is of course the whole point of these boundaries, that this mass should be negative. And then what are examples? Well, there are some examples, but maybe I'm not. Well, we kind of constructed already a coordinate system for that, and kind of built in this kind of a compactification here, this local resolution here, this conformal factor here, this phi.
Annegret, I mean, this is like a random question.
Yeah.
So I mean, because I think like a lot of the people, well, some of the people in this room, they like things like this, like
Yeah.
sort of you have some geometrical structure that is kind of asymptotically flat or something like
Yeah.
this, but it has to develop a singularity, and then
Well, the singularity is always there, yeah.
yeah, so but we like these sort of things, I think, like you kind of de-singularize in some nice geometric way. So I mean, there's like these things called like B geometry, log geometry. Things
I
like
don't know about that.
But we should chat maybe.
Yeah, maybe we should chat afterwards. No, I don't know, but yeah. So this later is just so this is just now a coordinate description of, you know, having some examples of those, and then you can show that, yeah, if you have this kind of cumulative mass function that has this asymptotics that r equals 0 and r equals infinity, because as I said, we're only looking at strictly symmetric models, then if it has this asymptotic behavior, then you can all, then you kind of have a model for such similarities. But it's very kind of it's kind of very hands-on. It's not a whole theory. It's just kind of constructing some examples that have this property. And the point is that you know, these models, they relate to these geometric invariant concepts that we already have. So it's the other way around in a sense. But then I think maybe have like 5 minutes or so.
No, but I mean, take your time.
Yeah. No, but I don't want to. I mean, it's a long day. So the point is that we kind of want to use this concept of these singularities to now derive a distributional Bianchi identity that includes these singularities. And so I'm just going to say a little bit more again about the framework of those. So okay, so we assume that we have a manifold which is diffeomorphic to R4. I write it here as M bar. And on this manifold, we have a smooth Lorentz symmetric of this particular form. So, you know, kind of build in that we already have what we want. That is smooth away from this singularity. And we can do we did this kind of coordinate change to kind of blow up this line to a cylinder. So it's just a coordinate transformation. I mean, the singularity is the same as it always is, but we kind of blow it up. To have, and the reason for that is because we want to apply a Stokes theorem, and for Stokes theorem you need to use codimension 1 boundaries, and yeah, that's the reason for kind of artificially blowing up this boundary. And so in particular, because it's smooth outside of this problematic region, every semi-Riemannian manifold satisfies the second Bianchi identity. So in particular, it holds everywhere where it's smooth. And the question is now, how do we include this boundary here, this zero area singularity? And how to derive a second? So essentially, the question is how to derive a second Bianchi identity for manifolds with boundary, with this type of boundary. And I'm just going to show you kind of a heuristic computation. I'm not going to read the whole proof, but this is now assuming that well, we have a manifold that is actually smooth everywhere, and we kind of, like in Minkowski's case, we kind of artificially create boundary there. But the metric is actually, nothing is wrong with the metric, nothing is wrong with the curvature in the singularity at all. And then here in the first step, we know that, of course, the Bianchi identity is satisfied pointwise everywhere. So in particular, it's 0. So here's a test vector field, like you would usually use in a series of distributions. You would use test functions, but now we use, of course, a test vector field because we have tensors. So this is 0 just pointwise, so nothing going there. Then we use integration by parts here, and then we use Stokes theorem here. Okay, so we go from M to the boundary, and for that it's kind of important to have this blow up procedure. But because I assume that actually everything is nice and smooth, and the boundary is codimension 1, of course, this is 0. And we are just kind of left with the second term. And so this is now an assumption that we have assumed that everything extends smoothly across the boundary. And this is of course not the situation that we want to study. So the first question was to define what a weak second Bianchi identity should even be. How do we want it to look like? And that's why we did this computation first. And then we said, well, if we do have a boundary and this kind of boundary integral is no longer well defined because something blows up there at the boundary, we can still kind of compute the limit. Just like we did for these zero area singularities, they kind of also were approached by surfaces where the area went to 0. So this is basically the same, also with a time attached to it. Okay, so this comes directly from this part, from this line here. And we call this the inhomogeneous version of the Bianchi identity. And we call it the twice contracted weak second Bianchi identity if this is 0. And the reason for doing that is because we are kind of dealing with very special kind of singularities that are zero area singularities. So it should be 0 because the area should be 0. And that the boundary data should be regular. Okay, so this is kind of a demand that we want it to be 0. And then our conjecture in a very general framework maybe is that if we kind of find admissible time-like singularities that are kind of modeling these zero area singularities and slices, then this weak second Bianchi identity should always hold. And we have proved this in a spherically symmetric static situation that I wrote here in this very kind of restricted framework, assuming that the metric already has this form. Then we could show that the weak second Bianchi identity is satisfied weakly if we have a certain decay at this singularity. And it looks like that. I mean, you don't need to look at the details of what I mean, it's kind of hard to read off. The point is that you need this decay in order for the limits to exist. Okay, and to apply essentially Stokes theorem again, all as I heuristically showed before. And of course the question is, well, okay, this is a very nice result, but is there any space-time that satisfies that, right? And the point is that yes, there are some. There's a corollary already that we have that if we have a space-time that has a mass function of the original coordinates, the area radius coordinates, that has this particular asymptotics at r equals 0, then already it's satisfied. So we only need to know the local behavior around this singularity to say whether it works or not. Of course, everything outside is anyway smooth. So this is like one particular case, but it still doesn't give you a concrete example. So now I'm just, in the last part, I'm just very quickly gonna show you that there are actually solutions to the Einstein equations that are of this kind. Okay. And the first one that one would like to use is what's called the Reissner-Wald-Lonsdam solution, which is a charged black hole, or in this case, a charged naked singularity, which has, in addition to this mass, also a charge. And here, okay, here I included all these physical constants. Okay, this is how we did it in the paper. I usually don't do that, but it was a physical paper, so I had to include the physical constants. So this is the one that you would like to use because you know it and everybody likes it and everybody studies it all the time and it looks very simple. but unfortunately, it turns out that it's too bad, okay? Because it comes from the Maxwell theory, and I already said that the Maxwell theory leads to infinite self-energies. And so this kind of shows up in the way how bad this curvature is. So this is the Kretschmann scalar, this is a curvature scalar, and it blows up at r to the minus 8, whereas for the negative mass Schwarzschild solution is r to the minus 6. So r to the minus 8 is too bad, okay? It doesn't work, and you can actually see that already a little bit, that this relative mass function has a 1 over r term. So if r goes to 0, it blows up. And you can actually, you cannot, of course, apply our result because it's only a, well, it's only a sufficient result, but you can actually prove directly that this solution does not satisfy it. And this is essentially also what the original Einstein-Infeld-Hoffman papers, they have somehow used that theory. So bad, okay. And but the good thing is that there are other electromagnetic theories that one can use, and it's good that my co-authors know a lot about those. So one of my co-authors has written an earlier paper where he defined an action, and you can then derive the Maxwell equations from that action. And usually you can also do that for the Maxwell equations, but you can also do it more generally. And in the way that you pick different Lagrangians, okay, not the standard one, but you pick different Lagrangian, and then you can he reformulated it as a Hamiltonian theory, and there are several conditions needed so to make it even a physically meaningful electromagnetic model. The first three are one that are always satisfied also by Maxwell's theory. And then we have two more conditions, which are related to having this finite energies and having sufficiently mild curvature singularities. And yeah, I have specific conditions here, but that's not, you see that they're not too complicated, but there's no point to discuss them. The point is that we want to use a theory that comes from a Lagrangian that has certain nice properties so that everything works out nicely. And the classical Maxwell theory doesn't work because it satisfies the first three conditions, but not the kind of nice singular behavior that we want. And there are other theories already well known actually by authors of this original paper that actually do work. And yeah, there are a lot of other theories which the Hamiltonian looks more complicated, but just to say that there are physical theories for which it works. And one can then show that indeed, for such theories, the twice contracted second Bianchi identity holds in the case where, well, you're electrostatic and spherically symmetric. And then the question is, of course, well, how to extend these results in more generality. So this is like, so this is called the Hoffman spacetime, which was already derived, I think I wrote here, in 1935 actually, from the Born-Infeld electromagnetic theory. And that is one example where it works, but it's not as explicit as the Reisner-Nordstrom solution. And it's a little bit, you see, it looks more complicated that there's an integral involved. And just heuristically, I want to say that we have seen that some singularities work and others don't. And the question is, well, when does it work and when does it not work in a more general setting? And the kind of only heuristic that we have is related to the Kretschmann scalar, which is this curvature scalar that blows up. And it shouldn't blow up too bad, but also not too good. So r to the minus 8 was this behavior that the Reisner-Nordstrom solution had. And it's bad because it's kind of has this infinite self-energy, which are minus infinity. And then we have this r minus 6 regime, which is essentially the regime of our theorem, where we have a finite negative boundary data and the Bianchi identity holds. And then we have this kind of in-between case where probably it works, but we don't have a general result. We have proved some special cases where
This -8, -6, -4 is for like this curvature.
Yeah, this is curvature. But you can actually directly relate this to this mass, to this SAS mass at the center.
Okay, can you relate to like the singularity of the metric directly instead of having to go through the curvature first?
Yeah. Well, it's in a sense, yeah, it's related to this. So the curvature is, I mean, it's a bit heuristic, right? But this m naught that I wrote here, this is essentially this cumulative mass at r equals 0, which is this SAS mass. And this does not involve curvatures. And because, so it's the limit of m of r goes to 0. And it essentially is, I think, r to the 3 of the square root of the scalar, the Krejci scalar as well. So there's this direct relation. So this is just to show that, yeah, strictly speaking, I think it's only the mass that matters and not the curvature. But in a sense, you do want to have a curvature blow up. So, you know, inside black holes, you often ask, well, you have a singularity, is it a curvature singularity? And so having a curvature singularity is a little bit more special than having, you know, some other kind of singularity.
But if we're to write just the metric tensor,
Yep.
like, what does it look like?
This mass, you mean?
Yeah.
Well,
What we mentioned before.
it's complicated. I mean, in a spherically symmetric case, it's yeah. Let's see where I had it. I mean, they have defined it in their paper, Bianchi, in a very general way with this local resolution. Yeah, so it's defined. It's defined like that. You have to pick a local resolution, and then you can compute it like that with your normal vector and with your conformal factor. And so,
Like to actually puzzle off what the metric looks like, G equals.
yeah. So if you have if you have a metric that looks like that, and then I have a particular example that the mass function is. So this is now in different coordinates. I kind of jump here a little bit. So this m of r is always, yeah, as written here, yeah. So this cumulative mass function is given in terms of these coordinate parameters. Then just go back here. So here, you see here.
So this is the expression for the metric.
Yeah, this is very symmetric, yeah.
R equals to 0 is a problem, right?
Yeah.
But just because of this r square in front of the.
But this is a spherical part, yeah. No, the problem is here.
all the
really.
problems there.
Yeah.
So
So you see that because this cumulative mass function, it contains this beta here. You can also write this differently, but I only wrote it here in coordinates. I mean, you could, you know, this is the usual coordinates that you use for spherical symmetry. So, so this is the problem. So the m of r. So if you go to r equals 0, then in the asymptotic expansion, this is the term that remains. And this is actually also, and this m of r is also in the spherical symmetric case exactly what's called the Hawking mass. So all these things have kind of a more geometric meaning that I wrote here. So it's the Hawking mass of these spheres. If r goes to 0, it gives you the mass of the singularity, and if r goes to infinity, the Hawking mass gives you the ADM mass. And this is also what you see, like in the negative mass Schwarzschild. That would be the m of r will be just the m will be just this constant. And if it's negative, it's negative, and then these two conditions are satisfied. But in the Reisner-Nordstrom solution, then it's exactly this problem that you have this 1 over r term, and then it blows up to minus infinity. And so you can kind of see that these conditions are not satisfied. But as I wrote here, these are only sufficient conditions. I mean, it's not optimal. Maybe it is, but we don't know. But we didn't really investigate it just because eventually, of course, we don't want to just stick to the spherical symmetric case. We just wanted to see whether, you know, kind of find out whether it works at all, basically. So we have some descriptions of when it works, but it's not the most general. So we have sufficient conditions for when it works. And I think if you want a general theory, then you have to go away from spherical symmetry and everything will be more complicated. And it will be a lot more complicated to compute this mass also. Maybe I just go to the last slide where I can summarize this now. So here, yeah, so this is like, essentially what we try to do is kind of come up with a general framework within which one could study the motion of particles, namely at this time like singularities that satisfy the second Bianchi identity. But we have only proven results in a more restricted setting. And of course, the question will be to generalize this, to more complicated situations. And also eventually to dynamical theory. And of course, in a sense, now I have always had one singularity that R equals 0. The real problem would be, of course, to study two singularities and how they interact. I mean, that would be, maybe you could almost consider that to be an analog of a two-body problem in this way of how you view the model. But there's a long way to go, I think. Okay. Well, thank you.
Thanks a lot.